James Brown.
Like I don't know who you are, James.
Yeah.
All right. Let's go over it, shall we? Okay, before we start into this, how many of you have been to see Mrs. Alex Winger?
She was supposed to call me back, never did.
Okay,
I sent him an email.
she's in room 217. You need to go get your advising so she can remove the hold from your advising record. Not only that, but she needs to fill out a degree plan with you, which we have not been doing here for the last 4 years, because I only found out about it about 2-3 months ago. Been asking the right questions for 4 years, and getting no answer, getting the deer in the headlights stare. Anyway, once you have that degree plan on file, then you can go in and take a look at it and see what your projected graduation is, and see what courses you're supposed to take next semester. The other thing it allows us to do, it allows me to push a button and figure out who should be in what courses next semester and next fall, etc. That's pretty important. That's getting more important because I did the analysis on Friday, and we had officially 31 juniors, slightly more than that, actually about 33 juniors this fall. Not everybody was taking every course that they should have taken because some were going part-time. But if we grow like we're thinking we're going to grow with all the people that we've got in the pipeline and everything, we could have as many as 60, close to 60 juniors next fall. And won't affect you because you're going to be seniors. There'll be room for you, but it's going to affect the other folks, and we didn't know. So it's one of those things we're going to get used to doing it right. So please go get your advising in the next 2 weeks, hopefully sometime this week. Okay. Our advising people will be on duty Monday through Wednesday of next week, even though you guys won't be going to school, so you can come in and get advising then. Okay? And I will be available probably through Wednesday noon, and if you need help with your project.
Yes.
Okay? Okay. We'll talk about all your advising stuff and everything when you go in and get your advising. All right, with that, let's go ahead and start with this. So your midterm is Wednesday, right? And as before, you will have an hour and 15 minutes, no more, no less, okay? Because we have a class before and a class after, okay? And so hopefully you have studied your brains out. Will it be like this? Yes, it will be like this. I will not give, no, it's not going to be exactly. It will be a gear train, okay? And it will use either spur or helical gears, either one. And you will be required to find the loads on the bearings. I probably will not make you find the diameter of the shaft. That would probably take too long.
Yeah.
So why did I do that? Why did I do that to you this time?
Because you're mean?
Because I could. Hey, you guys, it's the same reason soldiers join the army. They want to be soldiers. They didn't join to debate people, right? Okay, so you guys joined engineering because you want to be engineering, or engineers rather. So, how are you going to be engineers?
Join the army?
Just like pumping up those muscles, you know? You got to, no pain, no gain. All right. All right, so here's the problem statement. 80 kilowatts at 1800 RPM, module is 5 millimeters. Next time we'll probably do a module of 7 or 8. You probably should have been bigger gears, you know, but it works out. Phi sub n is standard, which is what? 20 degrees is the standard, okay? Other information per the diagram and the decisions, assumptions, the phi sub n, the phi in the normal direction, 20 degrees as we said. All right, so given that, first thing we're going to do is calculate all the torques and the speeds. So, how do we do that?
Start with the input one.
We don't cry.
We cried.
not wimps.
Tooth ratios.
What's that?
Tooth ratios.
We can take a look at the tooth ratio. So if we want to calculate the speeds, the quickest way to do that is to look at the tooth ratios. So you got 1,800 coming in, and you've got 20 and 50 teeth. So what's the RPM of this one? 20 over 50 times 1,800, right? And that gives us, you know, my little Excel spreadsheet here. This is one of those things that does nicely for an Excel spreadsheet. So you use one during the exam? No. Okay. Because I'm mean. All right, so whatever that is, and I don't have, I guess I didn't print that one. 720, right? Sounds about right. And then over here, it's 720 times 25 over 50, and that gives you what?
360.
360. Okay, so those are the RPMs. That one's answered. Now what?
Find the torque.
Well, first of all, yeah, we can find the torque. We've got everything we need for the torque. So the torque is equal to the horsepower, or the power rather, the watts over the omega, which is 80,000 divided by 1,800 divided by 60 times 2 pi, and that gives you
24.
424 Newton meters. Everybody get that? Okay, we're all looking good. I didn't hear any gasp, so.
That's what I did wrong.
Or did I hear some gasp? Somebody faint back here?
No.
All right.
My first mistake.
Now you gotta figure out what the, to get anything else, you really gotta figure out what the diameters are. So how do we figure out what the diameters are?
Use
Your little M.
radius.
Okay, so first of all, we know that M is equal 1 over P, right? And that the diameter is equal to N over P. And it's also equal to N over P cosine psi, which is going to be different for the high-speed side. This is the high speed, the low speed. Okay, so we could say that diameter is equal to Mn over cosine psi. So that's the equation that you should have been using. So given that, what's the diameter of the first, of the input gear, the driving gear? I
114.
call them gear 1,
Oh,
2, 3, and 4.
The gear or the pinion?
The pinion.
I got 114 millimeters.
You have to calculate M first, you don't have M.
Yeah.
M is given.
No, it's,
MN is given.
MN is given, and MN is normal, and M and MN are different.
M&M,
So-
right.
So M equals MN over cosine.
You gave us
psi.
a normal module.
Okay.
So if you calculate that, it's 5.697 millimeters per tooth.
Damn, I got it wrong.
5.697.
No, you didn't.
No,
Whenever
you
you
had
had
that-
your
you had
you
that
had
in
your
your spreadsheet, I
Excel
seen it.
sheet up, and it was the same as mine.
Was that?
hmm
You calculated
What
all that.
spreadsheet?
He had it.
Show
He
the
was
spreadsheet.
going through
Pull it
it.
up, it's on it.
Yeah, but I think I changed it.
I'm pretty sure you had the same numbers that I did.
I had the same diameters
It's
you
gonna be
did.
embarrassing, but that's okay, I can handle it.
Hey, I'm recording this too.
I'm probably gonna cry.
Yeah, see, you have
I
M
have
in there.
5 in here, is that what you guys got?
Yes.
119?
That's M.
That's what we got. That's what I
Yeah.
got.
Oh, yeah, okay.
And 5.7 and 5.3.
Yeah, so your D1 is 114.
So, yeah, so D1 is 114. All right, I got it right.
You got M,
I was wrong, I
there's your
got it right.
equation up there, M equals MN over cosine psi.
Okay,
But you also skip a step, because you have to figure out.
so what?
Skip
All right,
a step.
so the diameter, oops. Diameter 1 is equal to I got 113.9. Is that what you guys got?
Yeah.
Diameter 2 is 285. Diameter 3 is, oh, look at this. I'm not even in the presentation thing. Diameter 3 is 133.1. Diameter 4 is 266.1. Okay, so once we got that, then we can start doing some really cool stuff. So, this first gear is rotating clockwise as we're looking at it from the end, and the torque is going the same way. And so that's a characteristic you're going to see on all driving gears. Driving gears, the torque and the rotation is in the same direction. The driven gears, rotation and torque are in opposite directions, okay? All right, so then to get static equilibrium, I've got to have a tangential force at that point, at the top. And how do I calculate that? Well, I've got my torque.
Force times radius.
What's that?
T is equal to FR.
Ft is equal to the torque divided by the radius, R1. So that's 424, if I remember correctly.
Yes. Yes.
All right, divided by 113.1139, divided by 2, gives me 4, 5, no, let's see.
7.
7450. Okay. Newtons. Then the others, and that's from page, was it 682, I believe. Yeah, 682. All right, now, then because this is a left-hand thread, or left-hand gears rather, which go this way, then I've got an axial force, FA, which is equal to FT tan psi for these gears, which comes out to 7450 times tangent 0.5, which is equal to 4069 newtons. And then a radial force, which is Ft tan phi. So I got to figure out what phi is. So how do I get phi?
Tangent inverse. For the tangent.
Inverse tangent of tan phi sub n, which was 20 degrees, over cosine phi, which is going to be different for the high-speed and the low-speed gears. So phi for the high-speed gears is going to be equal to 0.393 radians. And phi for the low-speed gears, 0.37 radians.
A quick question regarding the standard 20 degrees.
Mm-hmm.
In the book, it doesn't specify phi sub n or phi, it just says, it almost makes it seem like the standard is for phi, not for phi sub n.
Yeah, except that that's true for spur gears, in other words, straight gears.
But it doesn't specify phi sub n.
Yeah, there doesn't, it really says that nowadays with the ability to do gear hopping and everything with CNC machines, that it sometimes is different. But the reality is that most gears are made by hopping machines, so 20 degrees is 20 to 25 degrees. It depends on what you want to accomplish. 25 degree will be a thicker, but then you're going to get more radial force. All right, so, once you have that, then, this becomes, 3089 or 3090 newtons. And so we've got all the forces we need on that gear. Now, those forces are gonna be reflected, equal and opposite, on the other gear, right? On the gear, this is the pinion. Okay? So that leads us to this next one, which is, how do we do this? Well, the rotation and the torque are both in this direction, 424. The rotation on this one is in this direction, but the torque is going to be this direction. Why? Because we have an equal and opposite tangential force on that particular gear, and so the torque has to be in opposition to that. So what's going to be the torque? 1061 Newton meters. And we can get that by multiplying the 7, what was it, 4, whatever, 7450 times the radius, which is, I think it's 266, wasn't it?
285.
285 divided into 2.
285, 122.5.
Okay, so then that means that the rotation on this pinion gear over here is in the same direction, obviously, as this one, and the torque is in the same direction, because it has to oppose that one over there. So, what I wanted you to see, that on the driving gears, the torque and the rotation is in the same direction. Torque and rotation are going to be opposed for the driven gears. Okay? All right, so the rotation in that direction. And the torque, we can get just by multiplying, torque is going to be double the one above, so the torque here is 2122 Newton meters. So we got a couple of things already answered. Any questions on that? All right, let's go to the, now we got to figure out what the gear forces are over here. So we know the rotation and the torque are counterclockwise, and this is a right-hand gear. Okay, so what's that going to do for us? I have to have a tangential force. I have to have a tangential force on this gear up here opposing that torque. So, did anybody figure that one out? It's just the torque divided by the radius.
Got 15955.
That's radius 3.
It's close enough.
15.9 what?
55.
Well, our, one of our other numbers was a little bit different than yours.
Yeah, I got 159.
Okay.
So that
1594 is close enough. 5540. Would I take any points off? No.
Just rounding.
Yeah,
He's just laughing at your error.
Depends on how. Okay, so now, which way is the tangential force? I mean, not the tangential, but the axial and the, of course, the radial. What happened?
Joel, don't break the chair.
He got the broke chair.
You got the broke chair?
I guess. Just lean back and
Little did they
It is
know.
not.
Is the chair actually broken?
I think so.
If it is, let's
I think
make
I've
sure-
sat in it before and leaned back.
Make sure you,
don't lean back.
no, well, yeah.
There's a switch
Make
that
sure you
turns
tell
that.
Steve
That
when
switch
is
is popped.
the,
Oh, it just popped?
Yeah.
One of these chairs over here?
Just don't lean back. You're
all
fine.
right, so the tangential force, same thing as before. I mean, the radial force is 15,940 times the tangent of .37, comes out to 6180 newtons. And then the axial force,
Yeah.
which way's the axial force going?
Out.
Okay? And that was 5820 newtons. And this gear down here has to be right hand or left hand?
Left hand.
Left hand. Okay, so now we got all the forces on the gears and everything, we can figure out what the forces are on the shaft. Okay, so we'll put those down. I use the convention of arrows, arrowheads or arrow tails, this being a tail, the other one being a head. And I also kind of draw it to the side like this, 7449 newtons. And 4069 newtons.
Can you give us isometric gears to draw on the test?
Can I?
Will you?
Yeah, but.
Will I? I have no idea.
What if we draw them up in SolidWorks and email it to
Okay, so
you
this one is going in, this one's coming out.
beforehand? Or I'll just print a stencil and draw my own.
Okay? Now, this says, this little force right here, this 4069 is gonna induce what up here? On the shaft, when we reduce it. Take the gears off. It's gonna give us a moment, right? And how do we figure that? 4069 times the radius, right? So it's gonna have a concentrated radius there, so just keep that in mind. Same thing with this one over here, although it's a much shorter, stubbier one.
Are they 382 and 5 or 5 something? I didn't write them down. What were they, Jared?
All right, and then this is coming out, and that's 15,947.50, whatever, going in. So that's kind of what I did on my paper, and then you don't need to figure out what these are down here because there's no bearings involved. The bearings here are here and about here.
I'll do that.
So with that, you can figure out a bunch of things. This is where it starts to get interesting. Okay? Okay, so what does this do? This induces a moment, concentrated moment right here at the point where the gear and the shaft are mated.
This is side view.
What's that?
That's all of it on there.
It doesn't matter. Yeah, this is the side view. It's all on here though. Okay, so now we've got 580 Newton meters here. That's what I calculated. Anything different?
No.
That's great, yeah.
And then this one right here is 387 Newton meters. And those only show up from the side. There's no concentrated moment showing up from the top. Okay?
That's your Y, X plane.
Yeah, so I labeled mine X, Y, Y, and Z coming out. All right? So what do you notice? Well, the nice thing about this is I've got this force and this force have a tendency to cancel each other. So I've got a net axial force in the going to the left of what?
17,
Yeah, it was 1700 something.
1756 is what I got.
I'll buy that. So that's the net. We're just going to kind of circle that, keep track of that. Okay, so how do we get the forces on the reaction forces on this puppy? Well, from the side, I'll do the blue here from the side. This is A over here, so this is R-A-Y and R-B-Y. Some of the moments about A, right? What'd you get for a reaction?
At B,
Yeah,
7,009.
So I got 7,020. And for A, I got 2259.
it's reasonable, and this one right here is 2258 is what I got. As long as you're close, give me a reasonable answer. Okay, now what?
Top view.
What's that?
Do the top view.
I can do the top view. Okay, and I'll put those in green. And let's see, top view will be going down, so I'll just put the answers here. Oh yeah, here we go. On the top view, I got 106 and 3608.
Yep. Almost 16,000.
I got 7527 and 15, 874.
Well, you know, pretty close. That's what I got. Is that what you guys got?
What direction?
I think you're starting to get some
Reasonable.
variations.
Slight variations. Okay, so let's talk about what the moment diagram from the side looks like.
What direction are those green ones acting?
Down.
Green, let's see.
Shaft is
This one is, yeah, this one is coming out. Oh, I'm sorry.
Can you draw up your,
Okay, that one's coming out towards us in the positive Z direction,
down, wouldn't it?
and this one is going in.
can you draw out your complete, XZ?
What?
Can you draw out your complete XZ?
Clean XV.
Your XZ
Oh, yeah, there it is.
diagram?
We'll do it on a separate piece. Let's just finish this one right here. So the shear and moment diagram.
Are you doing? Wait, yeah, because the other one.
Dr. Pratt, I think you're wrong.
What?
Said I think you're wrong.
All right, well, we'll check it out when we do the side, okay? I mean, the top. Do we all agree that at least the blue numbers are correct?
Your green values, what are your green values? Are those the reaction forces? and
Actually, those are-
XZ?
Those are from the top view.
And XZ?
Yes. Okay? So the shear moment diagram is gonna come down 2200, right? Shear diagram rather, and over to this point, and then up 6,178. So that's gonna make this minus 2258. And
And
that puts this
around
at
3,900.
3920. And then it's gonna come down 7,000. Okay, and then over and up. Okay, do we agree on that? puts these values in here at minus 282 and 784 and minus 309. And then if we do the moment diagram's gonna start down at minus 282. Then there's gonna be a concentrated moment that comes up above the positive. Takes you to 105. Then over to 889. Then down to 580, and then down to 0. Is that what you got?
That's the numbers I got. I forgot to draw my concentrated moment in there. So
Well.
don't take off for it.
Yeah.
Okay, so that's what I got. All right, so from the top. Okay, from the top we have a force coming out. It was 7449, right? And in at 15,947.
What do you have? We have, we got 7446 newtons up.
What's that?
We got that 7449 up.
No, it's coming down.
That's down. It's top view, isn't it?
Yeah, stop.
Is that right? I felt good
Don't-
about it when I did it. Okay, so some of the forces, it gives us a reaction of what? Are you looking at the right one?
Oh man. Maybe I am wrong.
Good.
Darn it.
I got 3608. Is that what you got? I got 12106.
That's good.
Can we go back to the FTs after
What's that?
which way they're?
Yeah.
I think I'm confused about the torque and the
Tangent force.
You wanna
Yeah.
go back?
Well, we don't have to right now. Just later.
Because I thought you
'Cause-
said the driving gear
Yeah.
is what,
Okay, so that, on that gear right there,
When they're different.
the
When the-
torque is going counterclockwise along with the rotation. That has to be reacted by that FT. So let's see if we got it right. Yeah.
but I thought FT,
Whenever you
The
had
FT
both
is
of
going-
them.
We're talking about the top gear here, because that's the shaft we're working on, right?
Well, what about the right side?
Yeah, the actual gear. Right here. That right there is where it.
Okay, this one right here.
No, not that one.
So the torque and the rotation are going to the right, the FT has to oppose it going in.
I get that, but why is it on a pinion and a gear they're different? Which way the torque is or something you said. Will you go back to where we had the whole
Where I'm
thing?
showing all the gear?
Yeah.
Right here?
Yeah.
Because when we did our, let's just do a quick one right here. So this gear is rotating, torquing this way, it has to be opposed by a force going this way, right?
Right.
That has to have an equal and opposite one here, right, which has to be opposed by a torque this way.
Okay.
So the rotation here, this is rotation, rotation this way, rotation and torque are different on your, and that cute little site that we gave you the link to, I printed this, I checked my answer against this, just to make sure. Okay?
What side
I'm not
is
above
that?
making mistakes.
What
I
side?
put my pants on one leg at a time, so I'm human. Okay? But I use this. You want me to pass this around?
Here, I got
What
one.
side is that?
What's underneath the banner?
You got email, or it's an
What's that?
update on the class page, you made an announcement on the candle line thing, that link, gives you a link to a PDF file.
They never, that's.
It's a nice PDF, except it gives things in kilogram force. What kind of unit is kilogram force?
So that's,
Dr. Pat, I have one question about that site, the PDF. It gives things in kilogram force, what is that?
What's
1,000
that?
grams.
It gives things in kgf. That's the unit.
Pound force, pound mass, kilograms,
It-
kilograms.
Yeah, I didn't know that metric had a kilogram
Kilograms.
force.
Kilogram.
You know,
Pound mass deal.
I think that's probably a typo.
Kilograms, roll around.
I'm pretty sure it said kgf.
KGF, KGM, same thing.
All right, let's take a 2-minute break. Mr. Regal, would you please go down, you know where the techs are? They're in the room right next to the secretaries. Secretaries are in 217, it's the one right next to it.
Okay.
Go in there and ask one of those guys to come and remove this stupid thing from my screen. Thanks.
Can we have our papers back during our 2-minute break
Why?
to change them?
I was thinking too.
No.
Okay. So that pin.
All right, but you asked, so let me tell you what I'm doing with this. I only need 8 more points to give us an even 400 points for the homework, right?
So
All
it's
right.
not
However, this one's counting for 20.
Aww.
bonus.
Hang
Anything
on.
over?
If you say "oh" after this, then I won't do that. But if you get more than 8 points, those are like bonus points. So anybody want to complain? I didn't think so.
Yeah, I might not get it.
You might know what?
I might get 8.
We might not get 8, so.
How many points total is it?
Can we only get
You guys are
100%
just trying to
homework
make me feel
average, or
bad.
can we
What?
get overage?
That pin, that first.
I know I ain't getting
No, I would get 8.
Oh, all of our other bonus stuff.
How much bonus did you have? Did you have?
Yeah, but we have to,
Like 4 points?
okay, so, don't overthink it. All right, so how do I figure out which way the tangential force is going? Very simply,
Have
I
a,
put the force on there that is needed for static equilibrium, okay? If I didn't have a tangential force opposing that torque, what would happen to the pinion? It would accelerate, okay? Theoretically infinitely. Okay, so don't overthink it.
But the tangential force acting on that shaft is in the positive direction.
guess you have to have a
You
torque
have
going
a
up
negative
for your
direction.
torque diagram, and then a torque going back down, so it
Okay.
makes sense, right?
Because it sounded like.
It's going in.
You have it as a
Wait a minute,
negative.
wait. You gotta do that wrong.
It was like years though.
No,
3? I was going.
Here you want the force on that shaft.
You didn't bring a copy?
Scanner downstairs was.
I know what I
Yeah,
did.
you were supposed to make a copy of it.
The scanner downstairs wasn't working.
It's going to figuring out, wait, here's the careful, so we're gonna do on the test, I'm good.
So how do I do
You
that?
just gotta get 8 points, man. Yeah.
Mm-hmm.
I'm not even getting 8 points on that.
I was like, what are they concentrating on?
I had no idea about the.
I didn't do nothing.
My numbers all match, my forces and everything, but they're.
So that messed me up was,
didn't do that much. I just did that straight in there. I didn't go up and then over. So maybe you won't notice. I did my first correct.
As long as we go to the village. No, wait, we have
When I got to the singularity function, my singularity functions, and I was like, oh, that one's not right. And I probably threw it. And I ended up getting a negative number somewhere. Wow. Negative I. Yeah, and it's, I don't think we'll have to do that. Oh yeah, because you already got it all calculated. I spent hours on that. This week? For electronics? Are you serious?
Oh, you didn't put it in. Yeah, you kept my chapter 12.
I thought it was just due by the end of this month. Our electronics project?
It's due that week.
I already know what I'm gonna do, it's just a matter of getting the parts.
What are you doing?
Just make a metal detector.
Metal detector?
The only reason why I do that is because my nephew wants one and I don't want to buy him one.
I was looking at megaphone.
For a metal detector? I looked online and they're like, we want the real one.
You've got the first step.
What do you need?
Wow. Little resistors, capacitors, depends on what you're
I'm doing a megaphone. I know. That would have been fun.
And I thought about, like, I found a video online where you can just take an old AM radio and a cheap calculator and tape them together. And it works as a metal detector. I thought about doing that as a joke in terms of the and I don't think Dr. Shin would think it was funny.
He'll be like,
Just tape them together.
that's all you gotta do?
A metal detector.
That's all you gotta do is tape it together?
Yeah.
That's all you have to do to get to it, is tape it together?
Yeah.
What, Amanda, are you trying to do like a crappy project? No, just, like, don't charge his project for the year. He's making some weird radio thing. He made like his own inductor.
Yeah, I
He made
saw
it like
that wrapping
huge and
around
crappy
the
looking.
Quaker.
I'm wondering if it even works, to be quite honest. Honestly, I don't really care too much. I'm just gonna be like, okay, Justin, what do you have? And then when he has it, I'm gonna write a really nice report about it and be like, this is what we did.
Hey, Brett, did you say you get pictures? You didn't get pictures, dude?
No, we, like 3 people went in and got their stuff. The same people were on there. The same people were on there for 1
One of the things I noticed, the reason why, when you calculate the concentrated moment, they come out as opposite signs that you apply to the diagram. You calculate the concentrated moment.
He was like, that. But I feel like he's just like.
Okay, at least he was
But
now, we watch videos twice.
they're both doing it.
And there's no time you don't have to play the game.
Keep going there.
That was so much fun. So much fun.
Dude, you wrote.
All right, folks, let's keep going. All right, does anyone have a question on which way these forces? I have argued this with Jared while we were taking our little break, and I am convinced I'm right. Anyone want to challenge it?
Yeah, the 744, I agree if your Z is down, positive, but then the 15 will go.
Well, because I'm looking, this is top, this is the top, I'm looking top down. So my Y was going straight up, and the right-hand rule says that my Z will be pointing down. Okay? So I've got the gear force from the 1-2 gear combination, 744 newtons pointing down, positive Z direction. I've got the pinion force that opposes that torque pointing up in the negative Z direction. And then I can do the sum of the moments again about A or B or whatever you want, you can check them. And I got 3608 reaction negative here and 12106 positive.
Can you explain why the 15947 is in the negative direction?
What's that?
Can you explain why the 15947 is in the negative
Okay,
direction?
one last time, we're not gonna argue, okay? All right. Here's the, remember we said that the torque and rotation were both counterclockwise looking at it from this end on the pinion, right? Gear number 3. That has to be opposed by a force on the pinion gear that we calculated at 15,940. My coordinate system is X is positive that way, Y is positive this way, and Z is positive this way. So it's opposite Z. Okay, there's my positive Z axis. Does everybody see that? Okay. All right, so let's move along. All right, so that gives us those forces, and now it's just a very simple shear
There goes some
moment
bonus
diagram.
points.
What?
So there goes some bonus points.
Okay, shear moment diagram, 1200 down, so that puts us 106 positive, then up 15,000, which puts it, I don't know, whatever the difference is, looks like 3 and some change, 3,800 or something like that. I didn't do a shear moment diagram on this. Then it's going to go negative some more up here, and then down 7449. All right, now, you can calculate all that, but really this one was just simpler for me if I just wrote the singularity function. Okay? Now, to calculate the shaft diameter, I wrote singularity functions. You can do it on your own, or do you want me to go through it? I mean, we've got time.
Singularity function. Let's go through it.
Can we go?
Let's go through it.
Well, we'll go through this one. Okay, so I'm going to erase the shear here because it's kind of getting in the way. Oops, I didn't need to erase that.
Can we go to where you tell us how you combine them to get the diameter? Or I don't understand that part. I still want to
Well,
know.
in fact, when I solved this thing, I didn't combine them. I just solved for the displacement in both directions. Okay?
On each singularity function.
Using singularity function. So this first one, D is equal to 12,106 minus 15,947. This is x to the 0. And this is x minus 0.125 to the 0. Minus 3608, x minus 0.325 to the 0. And the moment is just 12106 x minus 15,947, x minus 0.125. okay? And then I put EI theta is equal to 6053 x squared plus, no, minus 7974 x minus 0.125 squared minus 1804 plus the constant of integration. And then EI y is equal to these divided by 3, so that becomes 2018 x cubed minus 2658 x minus 0.25 cubed minus 601 x minus 0.325 cubed plus C1x plus C2. Then you can apply boundary conditions so that we know at this point right here, the displacement has got to be equal to 0, right? And actually these, instead of y here, there should be z, but.
Which one are we talking about? At the bearing or the?
At the bearing. So at R8, at y.
I thought it was at the gear, the
At zero.
displacement.
No, hang on a second, I've got to have a place where it's going to be 0, right? And the assumption is that that's going to occur at wherever the bearings are, okay? That, the displacement's got to be 0 there, otherwise I got a screwed up bearing. All right, so y at 0 is going to be equal to 0, correct?
C2 is 0.
Everybody see that? That means that C2 is equal to 0. Okay? Now, the other place it's going to be 0 is where?
At the other bearing?
Bearing B. Right, so y at 0.325 is going to be equal to 0. So I substitute all that in, and I get C1 is equal to 148. Should be negative, probably negative, because I got my sign screwed up, but it doesn't matter. Okay, so once I have the constant, then I can go in and I can say, okay, what are the displacements at my gears, right, or pinions?
0.0001 meters.
Okay, so I'm saying that y has got to be equal to 0.0001 as a goal. It's got to actually be that or less.
At 0.125.
Okay, and so I could say EI is that times EI, and then substitute in at the different points, right? So I end up with a formula that goes like this. Let's see. Okay? And then all I have to do, once I get the figure, is solve for D. So, on this side, at x equals 0.125, I got a D of 61.4 millimeters, or larger, and at x equals 0.425, which is this gear hanging out here, the D has got to be equal to 66.2 millimeters or larger.
Can I ask you a question on assumptions?
Yeah.
When we're looking at both the x, y, and the x and z plane, is it safe to assume that since on this XZ plane the forces are larger, that we should evaluate this shaft with the singularity function to get the higher?
Well, I did both. So I evaluated both directions, side and top, using singularity functions. Now, how do we do the other singularity function?
But I mean, to save time, can we make that assumption?
No, I don't think so. I think you gotta check it.
What do you mean how to do the other singularity function?
What's that?
What do you mean how to do the other singularity functions?
He's got to do singularity function for both x,
Oh,
y,
okay.
and x z plane.
Okay, so on the, that was from the top down. That one was the easiest one. So you might be wondering about the singularity functions on the other one. What's that? Okay, so singularity on the other, I wrote down V, let's see, we're gonna use blue one.
So that error on the shear moment diagram probably explains why I got a negative number on one.
Then you're gonna pick the higher, radius group, right? To
Yeah.
compensate for both.
Yeah. So I'm gonna just write down, I'm just gonna get you started on this. Okay, minus 7009, x minus 0.325 to the 0 power. Then you do the moment. Moment's a little bit different. So this comes out at minus 2258 x plus 6178 .
This is y, or yx.
Yeah. Now I've got to add in,
X,
I've got to add in something that's going to take care of my concentrated moments, right?
And I just beat it to zero, the,
Okay. So what I did was I added 387 x minus 0.125 to the 0 power. So there's my concentrated moment. Yes, I have a concentrated moment all the way out here at that gear, but it's at the end, and it never comes into play, so I only got to figure out one of them. So that's the beauty of this. Now, to check, because I'm known to make mistakes on occasion, I put in certain values, and I said, what are the moments at that point? And I did a free body diagram at this point, and I checked to see what the moment was. Okay, and it came out correctly. I also checked to see what the moment was out here. Okay, and it came to that concentrated moment that was out there. And you can check it out for yourself. If you take that and plug in 0.425, you'll get that 580 Newton meters out there.
what did you get for the diameter on this one?
Okay, so the diameters on this one, at x equals 0.125, the diameter came to 36.9 millimeters. And at x equals 0.425, the diameter required was 57.5 millimeters. So the point is that the largest of these is the one that's going to dictate our design. So, since I was interested in standard sizes for shafts that you can get out there, I said 70 or 80 millimeter, right? And I just picked that, 70 to 80 millimeter. And now I get to go and look and see what kind of bearing I need. Well, what are the forces on the bearings?
I have a question. Why 70 to 80?
Well,
What's that?
Why 70 to 80? What? How do you know what's the standard? It's in our book.
Take a look at your bearings. They go 70, 75, and 80 millimeter. Okay, so I need to have a shaft that will fit those bearings.
Why can't you do 60?
And in fact, I'm probably gonna have a larger diameter in here. I might have 100 millimeter. It depends on whether I'm weight limited or whatever. And I also have clear the gears. That's why I said I probably should have picked a modulus of 6 or 8 or something like that. You can put bigger gears on here.
So if we calculate different diameters here,
Wait a minute, one at a time. Okay, what was your question?
if we calculate different diameters based on our singularity functions, then should we create a step shaft based on those?
You could, if you're in a weight limited,
But if we're not weight limited, then we just go with the bigger diameter and have a straight shaft.
but you remember, we're only talking about the diameter at two locations. So the one that's governing happens to be this cantilever one out here.
Is that the bigger deflection gonna be
What's that?
happening?
Love thrust.
Okay, so let's talk about that. Let's talk about variance, because we got 10 minutes left, and that's about all we got time for.
Isn't the biggest deflection gonna be at that point where, that left here?
No. Turns out that the biggest deflection is gonna be on the right-hand side. Because that's the biggest diameter. When I was looking at it from the side, I got 57 millimeters for this one on the right, and 66 millimeters looking at it from the top. On the left-hand one, I got 37 and 62. Okay? So the biggest forces are looking from the top down. That just happens to be for this particular one, the key. So we pick, let's just say, because the shaft is not the big thing, okay? We just need that so we can pick the bearing size. So now, let's figure out what the forces are in the bearings. So bearing A. What are the forces? I've got a radial force on bearing A of 2258 and a tangential force of 12106 and an axial force could be 0, could be a maximum of 1752, right? Which is the difference between the two axial forces imposed by the two gears, either the pinion and the gear. All right? So an axial of 1752. All right? Well, what am I going to do with these two forces right here? Some of this, the square root of some of the squares. So the force that I was worried about, turns out the resultant is 12,315 newtons, and then I divide 1752 newtons to get the percentage, and I got something a lot less than 0.35. So if I look on, let's go back to, what is it, chapter 14. If I look on page 608 in the book, either a radial bearing or an angular ball bearing, either one will do, because the ratio of the tangential to the radial is less than 0.35, so either one will do.
I found on the internet that they use thrust roller bearings or something in
They could.
transmissions.
They could,
They're more expensive.
but if I'm not asking you to do that, I'm asking you to use ball bearings, because that's what's in our book, right? Okay, because you're gonna have an open book test. All right, so now, I know that FE is FR, and FR is 12,315. All right, so which bearings can work?
On the exam, can F equal A?
For ball bearings, 70 to 80 millimeter,
How often is it used?
oh yeah, we gotta figure that out, don't we? Okay, good.
Everywhere.
Yeah, you said, it was used.
All right, so we got the FE,
From this point, it's just a matter of opinion.
okay, so the C required is
I don't want to work.
12,315 times KA. What's KA?
It's one for roller bearing and a gearing application.
Okay, so it's for gearing, it goes from 1 to 1.3. So I'm gonna be conservative and take 1.3. Okay? And then I'm gonna use, I've gotta figure out what my life is. So if this is a machine that's gonna be used 8 hours a day, every day, every working day, then it's 20 to 30,000 hours. Again, I'm gonna be conservative, which is 30. And I multiply that times 1800 RPM times 60, and I get, let's see, 1296 times 10 to the 6 revolutions. So I put that in here. Divide by 90 times 10 to the 6, and then my KR is just 1.0 because I'm interested in the 90 percentile, right? And that's to the 0.3, and that gives me my C required of 35 kilonewtons. So now I can go and look. Thanks for catching me on that. Getting too far ahead of myself. Okay, so now I can go in and take a look. So which bearing is going to work? Well, none in the 70 to 80 will work, but the angular bearing will.
Why are we using 1800 when it's 720?
Oh, dang it.
Yeah, the shaft.
He's
is
being
720.
very safe.
I hate that when that happens. You caught me. Okay, I lose some points.
Does that mean we gain points?
It's all right. You can have those points.
You're gonna
back.
get
We can't.
points. All right, so that, you're right. Thank you, Troy. I'm big enough to admit my mistake. 720, which now comes out to what?
That. 1.296 times 10 to the 6.
1 point what? I don't think so.
1296 times 10 to the third, or 1.3 times 10 to the 6.
There can't be that much difference. It's about half that.
30 times 720 times 60 is 1296000.
Oh, this is 30,000, sorry.
Oh, 30,000? Okay.
Okay.
That's gonna give you,
1296 times 10 to the 6.
1296 times 10 to the 6.
Dang it, and I did it right.
You put the right answer,
You
the
just put the
wrong
wrong number up
steps.
there.
Yeah,
That's
the
what
wrong.
it is.
Yeah, I did.
Don't follow blind
said-
to the solution manual.
Okay, if you want to come look, it's right here. 720 RPM, dang it. Anyway, all right, so we still got it, I got the right answer. All right, so we still got to do 35 kilonewtons. So which bearing's going to work? The only one that's going to work is the angular ball bearing, alpha equals 25 degrees, 80 millimeter. So that's going to dictate the size of our shaft too. So it's going to be an 80 millimeter shaft, so we know just automatically that we're going to get less deflection than 0.1 millimeter, right? And this bearing is going to work. All right, then we go to bearing B, and bearing B comes out to less than that, 29.6 kilonewtons, C required. And
Can you use a
looks like we're gonna have to use the
85?
same one. Actually, we could use a 75, but just to simplify parts count and everything, we'll use the same one. So that's what I did. I chose an alpha 25 degrees, 316 bearing for both. That was painful. Okay, questions on that? So, in the test, I will not require you to figure out what the size of the diameter of the shaft is. But you are going to have to figure out what the forces on the bearings are, given the diameter, given the shaft, etc. Okay? Should not be too tough. You should be able to do it. So I would practice. You want resolving this, but forgetting about the diameter. Just assume an 80 millimeter diameter shaft.
Can you touch on the which bearings take the thrust or not.
Okay, so which bearing should take the thrust? What? Doesn't matter. I can place the bearing, if I use the alpha 25 degrees 316, I can place those bearings so they oppose each other and just lock the shaft in place. Then I don't have to worry about it.
But then you'd have to have, there's gonna be a result.
If I use regular, if I could get bigger, you know, heavy duty ball bearings, the ball bearings themselves would do it.
But there's a resultant thrust, so something has to counteract the thrust. So either
Yeah,
one
the
of them,
bearings will.
one of them has to
I
be thrust
recorded
bearing,
it.
or both of them have to be thrust